So dear students, let's continue our lecture about sets. Today we'll think about the size of sets, or more correctly, its cardinality. We show that our natural instinct about the relative size of finite sets can be extended to allow the comparison of infinite sets too, so sometimes with surprising results. So basically, natural numbers and sets of all rational numbers have the same size, whereas both these sets are smaller than the sets of real numbers. So what is actually cardinality of sets? The cardinality of a set is roughly the number of elements in a set. This poses few difficulties with finite sets, but infinite sets require some care. So let me read the definition of what is cardinality. Let S be a set, and if there are exactly n distinct elements in S, where n is a non-negative integer, we say that S is a finite set, and that n is the cardinality of S. Okay, so n is the cardinality of S. So cardinality of S is denoted by shorthand notation, and don't confuse this notation for set with absolute value of a number. How we can count the size of elements or size of a set which consists of elements? So let me provide some example. The first example is positive integers. Let A be the set of odd positive integers less than 10. So then size or cardinality size of a set A will be 5. Another example is instance of letters in any alphabet. Let S be the set of letters in the English alphabet. Then we'll have cardinality of a set of letters will be 26. Also, let's add information about cardinality in a null set. Because the null set has no elements, it follows that cardinality will be 0. Okay. So last two examples are about set of A, B, and X, which has cardinality size of 3, and cardinality set from A and B elements will be 2. So I can tell that two sets have the same number of elements by trying to pair the elements up. So when do two sets have the same size? Cantor answered this question in the 18th century, stating that two sets have the same sets when you can pair each element in one set with a unique element in the other. So let's consider two sets. First one is A, B, C, D. The second one is 1, 2, 3, and Kelvin. So they have the same number of elements because I can pair the elements of first set with element of the second. And this kind of pairing is called bijection or one-to-one correspondence. As you can see on the figure illustrated on the slide, I can pair first element A with the first element of a second set 1. Second element of first set B, I can pair with second element of a second set 2, and so on. And it is easy to understand it with finite sets, but we need to be more careful when we'll use this idea with infinite sets. Okay, so we'll review some definitions, results about functions. And what is the definition actually? We know that cardinality of a set is actually number of elements in a set. And two sets, we state that two sets A and B have the same cardinality if there exists a bijection. So basically the definition goes like this. The sets A and B have the same cardinality if and only if there is a one-to-one correspondence from A to B. And when A and B have the same cardinality, we write this kind of shorthand notation. Let's go with examples. Okay, I have two examples, and many people find this kind of example here surprising and concerning. But remember that our definition of same cardinality coincides with what we know to be the case with finite sets. We can prove, first example, that A and B, sets A, B, and set X and Y have the same cardinality without using the word 2 by pairing elements in the two sets, A with X, B with Y. And this is exactly how we argue, for instance, that in second example, that they have same cardinality, we pair 0 with 0, 2, 1 with 2, minus 1 with minus 2, 2 with 4, and with n, and so on. Let me go back to show, to repeat a few concepts. Basically, as we covered sets theory before, never forget that a finite set is either empty or 0 to or 1-to-1 correspondence with natural numbers. And infinite set that is not finite. So basically, infinite set is not empty set or with 1-to-1 correspondence with natural numbers. And cardinality of empty sets to be 0, and we write like this one notation. Okay. So for infinite sets, we have also this kind of definition. If there is one-to-one function from A to B, the cardinality of A is less than or the same as the cardinality of B, and we write that A is less than B. So don't confuse again with absolute value. And moreover, when A is less B, we know that A and B have different cardinalities, and we say that cardinality of A is less than cardinality of B. So we can write this way. And for infinite sets, the definition provides a relative measure of the size of two sets rather than a measure of size of one particular set. And one set has a smaller cardinality than another set. So let's try to solve examples which were different from theoretical and abstract concepts we covered before. And first example is problem shows that intervals between like -1 and 2 and -5 and 4 have the same cardinality. And it is important to notice that there are some closed or open intervals. And actually, how to go approach with this problem? So basically, let's go and overview solution, okay? So according to our overview, we should what to do? We should find a function according to the intervals, show that function is one-to-one, and show that the function is onto. So how we can do it? Let's have a function. So basically we have our intervals -1, 2, and the length of this interval will be 3 because 2 minus -1 will be 3, and the length of interval of second interval in a second set is 4 minus -5, so it will be 9, and the length of between two intervals is 3 and 9, and so there is a factor of 3 relationship, so triple relationship, and we can express the function like y is equal to 3x plus b. So since x belongs to interval -1 and 2, we can write this way. We multiply each side by 3, and we have -3 is less than 3x 6, and bigger than -3 and less than 6. So basically, to get this kind of values of second set, we just subtract 2 and we receive this kind of function. So this function will be a function according to that interval, and we have find and derived this kind of function, and the next step is to show that it is one-to-one. So basically it is one-to-one because a fixed domain and values are following the one-to-one principle and order. Another step is to illustrate the derived function is onto, since we get our inverse function, put values from y domain, and receive back its values of x. Okay, so if it's clear, let's move to another example where we can show that same problem but within closed interval. It is important that both of these intervals are closed intervals. If we say that it will be open interval, we can follow the approach in previous example, but we could have some difficulty, and we will see how to handle that kind of situation later. So let's break the task to simple steps. Find the function according to interval from f, find the function according to intervals from g, and show that f and g are inverses. So basically, two steps we covered before in the first example, and we can follow this same manner in our second problem. So we have another interval -3 and 5, which is closed, and it has length of 8. We have interval 0 and 4, which has length 4. How we find 8? So basically from 5 we subtracted -3 and we received it is 8. And interval from 0 to 4 has length of 4. So basically you can see between two intervals there are a factor of double relationship or two relationship. So we can write like y is equal to 2x plus b. Since x belongs to 0.4, we can find it. So we know that 2 times 4 is equal to 8, and we just scale it up by factor 2. And as it stands, we know that it cannot be 0 because f0 is not equal to 3, and we have to, I'd like to 0 to go to -3 in this interval. So I fix this by subtracting 3, okay? And we have that bijection, like f, we identified the function is equal to 2 times x minus 3, and since like f is belongs to interval minus 3 and 5 closed, therefore it is valid to write f is kind of bijection notation. As usual, I will show that f is bijective by constructing an inverse g, and you can do this by working backward on a scratch paper or doing a scaling argument like that one I used to construct in f. As I did with f, I need to show that g takes a supposed domain into domain of 0.0 and 4. And we have that it is 1/2 relationship because 8 and 4. So since x belongs to this kind of interval, we add on both sides by 3 and divide by 2, so we will have at output 0.0 and 4 interval. So our function, inverse function, will be x plus 3/2 gx. And since gx belongs to interval 0 and 4, therefore it's valid to write this way, okay, this notation. What is this? This is a bijection notation of g function. And the last step is to show that f and g are inverses. And as you can see, you covered composition of function before. We just put values of gx in f function, and we receive that composition f of gx will be x, and g of fx will be again x. And therefore f and g are bijections, and this is proof that this interval minus 3 interval like from minus 3 to 5 and from 0 to 4 have the same cardinality. So basically we learned how to prove our intervals that have same cardinality, and basically never forget this notation and what is the concept under this topic. So basically bijection and cardinality are two related topics, and you have to know about it, okay? So there is a continuation of this topic, like with countably infinite sets. We'll try to cover in another lessons. So thank you. If you have any questions, you can share your opinion. Goodbye. Have a good luck.